But what's a function? I think that's a good place to start. I mean, you could get real esoteric, very philosophical about it, but when it comes down to math, a function is just a rule. It's a rule that assigns, and then here's the part that makes it a function. It's a rule that assigns one output to each input, one and only one. So it can't give you two different outputs for the same input. So let me show you a couple of examples and a couple non-examples. So here are some examples of functions. Y equal to x squared, or f of x equal to 2x minus 1, or g of x equal to sine of 6x. All of these functions meet the criteria that each input, which we're usually thinking of the inputs as the x values, gives you only one output. Another way of saying that is that all these equations, all these functions pass the vertical line test. Meaning if you draw a vertical line, it hits at most 1 point on the graph. And you can look at, I mean, you can Desmos it up if you want. If I had opened it ahead of time, that would have been an idea, but it's taking a moment. I can also graph things, right? I mean, okay, real smart. Thanks. But yeah, these I don't. So right, y equals x squared looks like this. Very generically. Thank you, appreciate it. F of x equal to 2x minus 1 is a straight line. It's got a y-intercept of -1 and x-intercept of positive 1/2. And sine of 6x looks like a regular sine function with a period that's been smushed in. It's got a period of 2 pi divided by 6, or pi over 3. So pi over 3 is like 1-ish. So sine of 6x would look something vaguely like this. Oh, that's cosine, not sine. Good job. Sorry. Here we go, kind of like that. Welcome to Lawrence, joining us via Zoom. But the point is, each of these graphs, you can totally see that each x value on the x-axis, there is only one corresponding y value, right? If I go over here to some x value, I get one corresponding y value. And the same is true for all of them. On the other hand, and now I should kind of clarify here. Unless someone has said something else, we almost always make the blanket assumption that we're talking about y as a function of x. The independent variable is x, the dependent variable is y. That might change later on. Like I'm going to write something that I'm going to ask. So here's the question. Yes, I can see it. Okay. Is x equal to y squared a function? Well, in our context, no, it's not. If we draw it, it looks like this. Right, we could plot. I'm not anti-plotting points, but I only like to plot points because I'm trying to be very kind of precise. I'm just trying to get a general idea of the graph. Clearly, this graph fails the vertical line. I can draw many vertical lines, but I only need one that passes through more than 1 point. So this vertical line here, let's call it x equal to 9, passes through a couple points, 9, 3, and 9, -3. Also, just as a reminder, everyone, at some point, not right now, please mark your attendance using one of the QR codes that is hung on the blackboard, not the ones that are taped. For those of you joining via Zoom, follow the link in Canvas to, in fact, I should have the link ready. Next time I'll have the link ready. You can find the link in Canvas to mark yourselves present. So this is not a function as we classically think of it, right? Y is not a function of x. However, later on, someone might be, is that a function? And you're like, well, what do you mean? Because you could certainly say correctly that x is a function of y here. That would totally be accurate. But if we're talking about the usual, is y a function of x? Definitely not. there is, I would say, thank you, for each X input, there's more than one Y output. And that is the make or break kind of case. Right. So X equals Y squared, not a function. Another kind of great example of not being a function is a circle. X squared plus Y squared equal to, I don't know, 16. Looks like that. Definitely not a function either way, right? X isn't a function of Y isn't a function of X. But, right, Y is not a function of X. Doesn't pass the vertical line test, and we can see, well, and really, I mean, the thing I just said there, not passing the vertical line test, literally means the same thing as some inputs have more than one output. If you're not passing the vertical line test, it means there's an X value, X equals like 9, that has two different Y values associated to it. That's the same thing as what as I'm saying, right? You have one input and two outputs with it, doesn't work. So how can you tell? Question, yeah.
Are piecewise graphs functions?
Typically, yes. You can certainly make one that isn't, but the way that they are written, I mean, we'll do some examples. They're almost always written in a way that the domains don't overlap, so you never have this issue of one X value having multiple Y values associated with it. There was something else I wanted to say right there. Oh, the other thing is, how can you tell something's not a function without actually graphing it, right? Because maybe we don't want to graph it. So how can we tell that? I was going to use the same example, but fine. Let's do something. Oh, fine. I'll do something. X cubed plus Y cubed equal to 6xy. How can you tell that is not a function? May I see your symptom survey, please? It's not a function. How do we know? But I might have given myself another good example. Thank you. Well, if you can't solve for Y, it's usually a pretty good bet that it's not a function. That's not always 100% true, but here solving for Y is pretty much impossible, right? Like if like Y cubed minus 6xy equals negative X cubed, and then I'm going to see your symptom survey. That's what's going to happen. Thanks. Right? This is garbage. Because I can't divide by Y squared minus 6x, because then Y is a function of Y. So sometimes you kind of are stuck graphing. And graphing this is not particularly easy. This is why Desmos is a great tool, right? Because sometimes, like the other things, no problem to graph. X equals Y squared, circle. But this thing, not so easy. But we can graph it. And 6xy. Kind of cool, right? And now, very obviously not a function. But it would be hard to tell because, I mean, really, there's only really two nice points on this function. One of them is the point 0, 0. The other one is the point 3, 3. That's kind of it. Every other point is kind of terrible. And so you might have to just graph it and see whether that's function. But typically the idea, like for example, how would you tell? This one you would have to graph it. Use Desmos. That's the other thing that's nice about Desmos versus like a regular graphing calculator. Most regular graphing calculators, at least maybe they've gotten better. I don't know. It's been a while since I've really used one. Usually you're stuck with like Y equals whatever. Right? That's the typical prompt. Whereas in something like this, you can totally graph whatever equation you want to. So again, I know I've said it a couple times. I'm going to keep saying it. You should really get comfortable using Desmos if you haven't already, because it's a wonderful program. Another example of mine. Sure. What about this one? What about brain? Sure. X equal to Y squared. Yeah, minus 2Y minus 2. Oh, yeah. Thanks. You should always just let me know. I will make that mistake more than I care to admit. So how do you know this isn't a function? Well, there's a couple ways. One way is obviously it's a sideways parabola, right? We know the graph of this. We know, oh, my hands a little too much, all right. But let's say you didn't want to graph it for real. Well, you could try solving for y here. It's a little bit of a pain in the butt. And I'm going to add 3 over here. X plus 3 equals y squared minus 2y. And then to actually be able to solve for y when you've got something quadratic like this, you have to complete the square. Luckily, it's not terrible here. Completing the square, you take half of -2. I wish I had my red pen. Divided by, so half of -2, and then you square it. And that's what you add to both sides. And whenever you're messing with an equation, you send it to one side, you add to the other side. You can either add 1 here and add 1 here, or you can add 1 here and subtract 1 here. It doesn't really matter. There we go. I did it to both sides. It looks, I know this looks kind of not the best. So I've got x plus 4 on the left. And on the right, the reason we added 1 was to complete the square, right? It's now going to look like something squared. It's going to be y minus 1 squared. And now I can try and solve for y. And here's kind of the big catch. When I do this, right, this is the class we had the big discussion about square roots in, right? Is it? I don't remember. No, okay. I was like, there was one of my classes the other day. I was like, we were talking about all the square root things. It's not this class, I remember now. If you're trying, so actually, let's take a quick, we'll come back to this, I promise. Let's take a quick journey down the square root path. And this is going to feel like a dumb question. What's the square root of 9? Thanks. Okay. What are the solutions to x squared equal to 9? Right. -3 and +3. Now here's why, or what's going on. To solve this, you could bring the 9 to the other side and factor, but we're not going to do that. We're going to square root both sides. All right, you all just told me accurately the square root of 9 is 3. What's the square root of x squared? Well, some of the time. Some of the time it's definitely x. Some of the time it's -x. Really, what the square root of x squared is a piecewise function. We'll talk about it in a minute. The square root of x squared is the absolute value of x. Let me give you some proof for that, because I feel like you might not believe me. It's all right. What's the square root of 5 squared? I think you guys know it's 5, right? Okay, slightly more challenging question. What's the square root of -5 squared? It's not a trick. I mean, it's kind of a trick question, but it's not that tricky. What's -5 squared? What's the square root of 25? So this is a function, the square root of x squared, that when you input a positive number, it gives you back the same positive number. But when you input a negative number, it gives you back the corresponding positive number. And we know another function that does that. It's called the absolute value. So it's worth knowing that the square root of x squared actually is the absolute value of x. And now, if we're solving the absolute value of x equal to 3, thank you so much. We're going to get x equal to either +3 or -3. Okay, so when you're solving a square root equation like this, right, when you are, back to this, when you are square rooting both sides, what I really should be doing, the right side, the square root of y minus 1 squared is really going to be the absolute value of y minus 1. We're going to skip all that though. And we're going to be like, we know that when we square root both sides, the side that isn't the square side gets the plus or minus. So it's a plus or minus square root of x plus 4 equal to y minus 1. Or solving for y completely, it's a y equal to 1 plus or minus the square root of x plus 4. And that's a problem. Specifically, the plus or minus is the problem. Because now, for example, if x were 0, y could be 1 plus the square root of 4, which is 3, or 1 minus the square root of 4, which is negative 1. One x input corresponds to 2 y outputs. That means it's not a function. So most of the time, if someone is asking you to show without a graph, I don't think this is really going to come up that often, but it might, and it's worth addressing anyway. But if someone says show something's a function, or sorry, show something's not a function without graphing it, I don't know why they do that really. But usually you're looking for something like this, looking for a plus or minus to pop up, because that's showing you, oh yeah, I'm getting 2 different values of output for this one value. There are other things, but that's mostly the thing that happens if you're trying to show something's not a function. Okay. Yeah. Okay. And I had, where'd I put my links? They're hiding from me. They're right here. Cool. Also, if you guys see something come up in the chat, let me know, because I often don't see it because I'm looking like over here and down here. Yeah, let's talk about domain and range. It's more generally domain, really. Like domain's kind of the bigger deal, but range is also important. And sure. Or even equations. So you can talk about the domain and the range of something that is not actually a function. Because we're talking about domain, you're really just talking about all the x values, all the possible x values. And we talk about range, we're talking about all the possible y values. So just as a point, that equation right there has a domain and a range of all real numbers. Right? I think we can agree that x can be anything, right? This continues going off that way and down that way. X can be any negative or positive number, and y can be any negative real number or negative or positive number. So for the not function, for the equation, and I know you can't see, for the equation x cubed plus y cubed equal to 6xy, the domain, you can either write it as parentheses negative infinity to infinity. That's all real numbers. We never give, so parentheses means you don't include that number, and we don't include infinity because it's not a real number. It's just a direction or an idea. You can also write the set of all real numbers as this fancy R. It's just an R with an extra vertical line. Or you could literally write out the words all real numbers, but that seems like way more work than any math person would ever do. The range would be the same. Let's look at one more equation before we start talking about functions. How about this one? X minus 3 squared plus y plus 1 squared equal to 25. What kind of thing is that? It's a circle. What's the radius of that circle? What's the center of that circle? Thank you so much. Yeah. So I don't need to draw it, but I'm going to draw it. Center over here at 3, -1. And then the radius is 5, and I'm going 5 in each direction. So 5, 5, 5, 5. So if that's 3, -1, the domain is as much as 5 to the left and 5 to the right of 3. So my domain here would be, let's see, 3 minus 5 is -2. 3 plus 5 is 8. Right, this point over here would be -2, -1. And this point over here would be +8, -1. The range, well, the y values go as low as what? -6, and -1 minus 5, and +4, -1 plus 5. All right, we're just talking about all the allowable x values, all the allowable y values. This equation, right, not a function. This equation, that's what its domain and range are. Those are all the possible x values. Those are all the possible y values. And I should mention, this does mean literally every real number between -2 and +8, right? That's all the decimals, all the fractions, all the irrational numbers, right? Square root of 2 is in there, pi is in there, all kinds of stuff. So don't limit your thinking to just integers, right? It's not just -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, right? It's all the things in between as well. Literally an infinitude of choices. Let's talk about the more real deal with domain and range, which is let's look over there. Let's say we had a function like this. We wanted to find the domain of it. And range is kind of, I'm not gonna lie, range is a pain in the butt. Depending on the function, it can be not terrible. A lot of the time for the range, you just have to graph it and see. And graphing this might be somewhat challenging. Let's see. So for domain, there are typically 3 things you're not allowed to do. Here, what are we not allowed to do? Yeah, exactly. So we know that the denominator, I just say we like to exclude where the denominator is equal to 0. Right? Usually when we talk about domain, we actually really talk about what's not in the domain and then say it's everything else but that. So here, I don't want x minus 4 equal to 0. You could either factor this. That's probably the more way of doing it. So we want to exclude the values of 2 and -2, and just those values. So if you're looking at the real number line, we don't want those, but we literally want everything else. So here our domain would be everything from -infinity to -2, excluding -2 with the parentheses, union -2 to 2, right? Excluding the endpoints, but we want all the values between -2 and 2, so -1.9, -1.87, -1, all the things up to +2, but not including it. And then everything from 2 onward. There's our domain written in the interval notation. And in my opinion, and not really my opinion, it's more that I know your math teachers will probably want you to do it this way. This is the way you probably should get used to doing it. Right? There are certainly other ways of doing this. Some people might write something like the set of real numbers minus the set containing -2 and 2. No one wants you to do that. It's correct, but it's not what people are looking for. So I would encourage you to do it like this, not like this. And you probably, it's usually not sufficient just to say like the domain is x not equal to ±2. People know what you mean there, but they want you to write it out. The range, on the other hand, I mean, I could graph this function, but I don't really want to. Let's take a look. What have I got? X of x plus 3 x squared minus 4. Interesting. So the range here is complicated. It's not beyond our ability. Well, it's not beyond our eventual ability to find the range of this, but we currently don't have the tools to really find the range because we don't yet know how to find maxes and mins. We're going to learn that for sure. So I can see looking at this graph, and this value does not say anything to me. Right? That's a number that's probably some irrational number. I don't know what it is really. But if you wanted to use this graph to say what the range was, you can zoom out a little bit. It looks like the range is everything from negative infinity up to this y value here, negative 0.655. I'm gonna go look at this later and be like, what's that number actually? Right, because that's probably not where that decimal really terminates. And then everything from this, what I assume is the lowest point in this part here, negative 0.95, sorry, 0.095 to infinity. Kind of neat. I mean, so you can totally use Desmos to see what the range of a function is just by looking at the value. And the nice thing is it will tell you where the relative maximum or relative minimum of a function is in a particular area. But no one's gonna ask me to find the range of this. Like it's not a good question. Let's look at some other examples. Let's look at some other examples by actually seeing them. Yeah, sure. So let's look at something like g of x equal to the square root of, sure. Let's just factor it. 6 minus x times x plus 1. And so one of the things we can't do is divide by 0. Another thing we can't do is take the square root of a negative number. And I should say, we can't divide by 0 because dividing by 0 is undefined. We can't take the square root of a negative number because when you do that, you get an imaginary result. And when we're talking about functions, we're always talking about real value functions, meaning the outputs have to be real, non-imaginary numbers. So here, when I see something like this, I'm going to set the insides, 6 minus x times x plus 1, to be greater than or equal to 0. Also, I will mention I am going to post these notes after class, so if you miss anything, it will be there later. You're also, if you miss something, you'll be like, hey, James, what was that? I want to know when this thing is greater than or equal to 0. I'm going to use the number line. And I'm going to put on the number line the things that make it equal to 0, specifically positive 6 and negative 1. And I'm going to test a point in each of the intervals. So I'm going to test something like 12 or 7, right? 7 is the boring choice, like something bigger than 6 would be 7. Or 7 million, right? It doesn't matter. Any of those numbers that are bigger than 6 will yield the same result, whether it's positive or negative in that region. So I pick something like 7. 6 minus 7 is negative. 7 plus 1 is positive, and a negative times a positive is negative. And then I pick something between negative 1 and 6, like 2. 6 minus 2 is positive. 2 plus 1 is positive. Positive times positive is positive. And I pick something like negative 2. 6 minus 2 is positive. Negative 2 plus 1 is negative. Positive times negative is negative. And I want where this quantity here is greater than or equal to 0. So my domain here is everything between negative 1 and positive 6, including those endpoints. So I use brackets, right? I want to include negative 1 because negative 1 is allowed. If you plug in negative 1 for x, you get the square root of 0, which is 0. Totally valid. Plug in 6 for x, you get the square root of 0, which is 0. Totally valid. But we can't take the square root of negative numbers. On the other hand, if our function was, say, something like the log base 2 of 6 minus x times x plus 1. The domain would be virtually the same, but slightly different. Because when you have a logarithm, we can only take the logarithm of positive numbers. You cannot take the log of 0 or a negative number. I can talk about why if you want, but right here the domain is going to be setting all of the arguments or the inside of the logarithm to be strictly greater than 0. We've already done the work for that, right? It's literally right up there. But now we don't want to include the endpoints because including 6 or including negative 1 would mean we are taking the log of 0, which isn't something we're able to do. Murder this. This document camera is accidentally here, sorry. Stabbing with my pen. So here, our domain would be negative 1 to 6, exclusive of the endpoints. We don't want to include them. Sure. Let's look at one or two more examples. I didn't talk about the range of either of these because they're just kind of. Let me look at it. Yeah, I've got two more examples. One, and at least one of them we can talk about the range. So let's look at this example. H of t equal to the square root of 9 minus t squared. This one we will also talk about the range because it's worthwhile. Well, it's not that it's worthwhile, it's that we were able to actually, is the real answer. So here, domain, we're going to be setting the insides to be greater than or equal to 0. You could, if you wanted to, isolate t squared here, but it's a little dicey. If you wanted to, you could say, okay, 9 is greater than or equal to t squared. Take the square root of both sides. So 3 is greater than or equal to the absolute value of t, which would mean t has to be between 3 and negative 3. Right? T couldn't be 4. T also couldn't be negative 4 or negative 3.5 or anything outside of that range. So you could do it this way, but if it's inequalities of square roots they can go sideways real quick. So if I were doing it, I would recommend factoring. I would factor this as 3 minus t times 3 plus t greater than or equal to 0. And then on my number line, I've got a positive 3 and a negative 3, because those are the values of t that make the whole expression equal to 0. And then I'm just picking numbers. Pick 4, negative, positive. Pick 0, positive, positive. Pick negative 4, positive, negative. And I want this and the endpoints. So here my domain is everything from negative 3 to 3. And here we can talk about the range, because in this particular problem, it's relatively easy to see what the biggest this function can be and what the smallest this function can be. So for h of t equal to the square root of 9 minus t squared, what's the smallest output a square root can ever do? Can a square root ever give us a negative result? No, right? We talked about square root of 9 is 3, not negative 3. So what's the smallest number we can ever get out of a square root? Smaller? 0. 0 is the smallest number, right? It's the only number that's not positive. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. And so on and so on. So 0 is your smallest output. So is there a number we could pick for t that would get us 0? Totally, yeah. So 0 is in the range. So the range, you can think about the y value. Wow, that's beautiful. The range, the y values certainly have to be bigger than or equal to 0. And we can get 0 for sure. What's the largest y? And I know I'm using y kind of interchangeably with the function name here. What's the largest y value you can get? Well, to make this thing as large as possible, if I'm subtracting off t squared, I want to make t squared as small as possible. What's the smallest t squared can be? Could it be negative? Can t squared be negative? I don't think so. I should say, if you're picking real values for t, it cannot. If you pick an imaginary number, okay, an imaginary number squared is negative, but we're not going there. The smallest t squared can be is 0. 0 squared is 0, and any other number squared is going to be larger. So the smallest value can be 0, which means the biggest the insides can be is 9. And the biggest this value can be is the square root of 9, which is 3. So our range here is 0 to 3. You can also see it graphically, right? If you graph this, if you maybe think of it more as y equal to the square root of 9 minus x squared, and then maybe square both sides, and then maybe add x squared to the left and get x squared plus y squared equal to 9, you might see that, oh, it's a circle of radius 3, except it's just the top half, since the outputs have to be positive. So this looks like this, or better. Top half of the circle of radius 3. Definitely has a domain from -3 to 3. Has a range from 0 to 3. Nah. This is going to be just excellent the whole quarter, I'm sure. Oh my God. Okay, sorry. Oh yeah, I had one more. Domain and range, and then the time. Okay, yeah, we can do that. Sure. Let's look at this one here. Let's look at g of x equals to x plus 1 over 4 minus the square root of x. So we have a couple domain things happening here at the same time. First and foremost, the insides of a square root have to be non-negative. So we know right off the bat, x has to be greater than or equal to 0. But then we also have at play the possibility of dividing by 0. So we also need that. We have to exclude where the denominator is equal to 0. And that's going to be when x is 16. Right? If we solve for x, 4 equals the square root of x, and you square both sides. So our domain here is x has to be bigger than or equal to 0, except it can't be 16. We could draw it. I like drawing it. Like, you don't have to draw it, but I think it's kind of useful to draw it so then you can maybe, it just helps you do it, right? So I want 0, I don't want 16, and I want everything that's bigger than, meaning to the right of 0, but not 16. So my domain here is 0 inclusive to 16 exclusive, union 16 exclusive to infinity. And infinity is always exclusive. Very exclusive. Like, yeah, I'm the best. You can't be with me. I'm infinity. Yeah. Sure. Yeah, let's talk about piecewise functions. And I'm going to start off by talking about what I think is probably the most important piecewise function you will ever use. F of x equal to x when x is positive and negative x when x is negative. And it can be equal to either one, because whenever x is 0, either way it would be 0. How would I graph this function? Well, I want to do not all the work in the world. Like, you could totally, I'm going to do this long way this one time, and then be like, you shouldn't do this. You could graph y equals x, the whole deal. There it is. You graph y equals negative x. And then you can ask yourself, okay, from these functions, which parts do I want? Well, I want y equal to x when x is greater than or equal to 0. So I want this graph only to the right of 0, including 0. So I want all of this. I want y equal to negative x when x is less than 0. So I don't want this point here, although it's going to get filled in right there. But I do want all of this. So all of the green squiggly part is the part that is actually going to go on my piecewise graph. And I should say, right, here's x greater than 0, greater than or equal to 0. Here's x less than 0. So I want all of this when x is less than 0. And then I'm going to fill that in. I want all of the other part when x is greater than 0. And it looks maybe not as nice as I would have liked it to, but there's our function, also known as the absolute value function. So I should really strongly emphasize this absolute value notation is perfectly lovely, we use it all the time, but it's really just an abbreviation for this bigger piecewise function. So when you see this, you should think, oh, I really have this thing where if the insides are positive, leave it alone, you get what you already had. But if the insides are negative, multiply by -1 to make it positive. That's the whole deal with an absolute value function. And you can do it for all sorts of things, meaning it doesn't just have to be the absolute value of x. You could have the absolute value of x minus 3, for example. And we can make that a piecewise function real quick. It's going to be leave it alone if it's already positive. I'm going to say not negative. Multiply by -1 if the insides happen to be negative. That's how piecewise functions, or that's how absolute value functions always work. And then you could do a little bit of manipulating here, where you could say this is really, it's x minus 3 if x is bigger than or equal to 3, and it's negative. You can even distribute the -1 if you really wanted to. It's negative x plus 3 when x is less than 3. It's really just the absolute value function shifted 3 to the right. So this looks like this. Oh, or kind of like that. It's got a y-intercept of 3, and an x-intercept of 3. Kind of cool. But these are not the only piecewise functions you have to deal with. Somebody asked about this one. And yeah, let's go ahead and look at this one. So the next one we're going to look at is, I think, that, and you should correct me if I'm wrong, I think what they were trying to get across was a piecewise function is e to the x squared minus 2. I'm not sure if the minus 2 is in the exponent or not. Anyone know? Okay. I feel like it maybe, I feel like I could go either way. I think I want it not there. I think I want it down here. If x is bigger than 0, and it's equal to 4 plus x if x is less than 0. I didn't see an equal sign on either one of them, so I'm going to put it here. So let me rewrite this a little bit, because so normally when I write a piecewise function, I typically write it from left to right, meaning the part with the leftmost domain usually goes on top. So this part here is the part with the leftmost domain. When x is less than 0, and this part here has the rightmost domain. So I would probably actually usually write this as f of x equal to 4 plus x, if x is less than 0, and e to the x squared minus 2, if x is greater than or equal to 0. That's how I would write it. Now I want to graph it. And honestly, I don't want to do all the graph. Like I really don't want to, if I can help it. I don't want to graph 3 different things, right? We have a limited amount of time in our lives. I don't want to spend all of the graphing things. I could. It would take forever. So what I want to do is say, I only want y equals 4 plus x when x is less than 0. So I'm going to think about what y equals 4 plus x looks like. Okay, y equals 4 plus x. It has a y-intercept of 4, or would if we actually got to the y-axis. Has an x-intercept of -4. -4 is okay because -4 is less than 0. So x can be -4, that's totally fine. So I would get the points like -4, 0, and -3, 1, and -2, 2, and -3, 1. Sorry, -1, 3. And I wouldn't quite get to 0, 4, but it would be open there. There is the left piece of my piecewise function. And I definitely do want to make note of, even though this point isn't included, it's like the end of that part, and you should probably label it. I know the point 0, 4 isn't actually part of the graph, but it's the boundary of that piece, and it's worth noting. And then e to the x squared minus 2, which I actually don't really have a good concept of what e to the x squared looks like. Let's take a look. That's kind of bonkers, okay? And check this out. You guys should all watch this. They said don't be in the exponent there like that. Be smart. Look at that. Piecewise function. In fact, you can even make the whole piecewise function on Desmos. And cool. We zoom. Except I got my equals sign in the wrong spot, right? My function should have been x greater than. So if you want a greater than or equal to in Desmos, you type the greater than symbol and then you do the equal symbol after, and it just changes it into the greater than or equal to. I was getting there, but thank you. Yes, I appreciate it. And then really what I was actually doing before I got carried away here was I really just wanted to see what e to the x squared looked like, and then I was going to draw it myself. But you're right, we could totally shift it down too, and that would be the piecewise function. The point I was trying to get at is, so let me undo that. E to the x squared looks vaguely like that. And specifically, it has a y-intercept of 1. So I know that e to the x squared, or I should say e to the 0 is 1. So I know that this is going to be, well, if I plug in 0, I'm going to get 1 minus 2, which is -1. And then I'm going to go to the right, and it's going to look like that. Sorry. It's going to look like that. So it's going to do something like that. It looks kind of parabola-ish. It's not a parabola, but it kind of has that look to it. If I were assigning this as a homework problem, I would probably expect people to find this x-intercept here. It's usually something people are looking for. So how do we find the x-intercept? We set y equal to 0, or the function equal to 0. Specifically, we're setting this piece equal to 0. So I'm going to solve for x. So e to the x squared equals 2. And then how am I going to solve for x squared? What do we do to get rid of an e? Take the natural log of both sides. And then the natural log of e to the x squared is just x squared. What I like to say is the natural log of something and e to the something undo each other. I hesitate to use the word cancel. You can also think about the x squared coming down in front here. And you have x squared times the natural log of e. And the natural log of e is just 1. Because the base is e, and you're asking the question, e raised to what power equals e? Oh yeah, the power is 1. So then x squared equals natural log of 2, x equals the positive square root of the natural log of 2. Right? It's not plus or minus here, even though you would normally do that when you were solving x squared equal to a number. It's not plus or minus because we know that this function is only when x is positive. Whereas if you were actually graphing the whole entire thing, not the piecewise thing, where'd you go? Right, then you would have both the square root of the natural log of 2 and the negative square root of the natural log of 2 as x-intercepts. Yeah, piecewise function. So what I'm trying to say is you want to graph a piecewise function by kind of just, let's look at one more. I know it's like 258. I can squeeze in one more example. Definitely. Let's do one more real quick example. Let's say we want to graph f of x equal to 4 minus x squared when x is less than or equal to -1. 3 when x is between -1 and 2, and 6 minus x when x is bigger than or equal to 2. Here is a piecewise function. And I guess the point is you have to kind of know what graphs look like, right? To be able to graph piecewise functions efficiently, you have to know what all the individual pieces look like. So I know that 4 minus x squared looks like this, right? It's got a y-intercept of 0, 4. It's got x-intercepts of plus or minus 2. And y equals 6 minus x looks like that. And it's got intercepts of 6 and 6. And y equals 3 is just a nice horizontal line at 3. I'm not even going to draw. And then I'm just going to, I feel like the word just is not the right word there. I'm going to, right? It's not just, it's the process. I'm going to draw this section until I get to x equal to -1. So I want all this graph up until I get to when x is -1 and y is 3. Okay, and then from -1 to 2, I want the horizontal line y equals 3, which happens to meet up with that point there. Like there isn't any jump discontinuity. So it would have been open there, but it's already closed. And then after 2, I get y equals 6 minus x. So I don't actually have this point right here, but it would start, right there. Whatever. What point would that be actually? When x is 2. Well, if I'm graphing 6 minus x and x is 2, y has to be 4. And then it's just going to continue down this way, hitting my x-intercept over here of 6, 0. So that's how I would graph this piecewise function, using the knowledge of other functions I already have about what they look like, and then grabbing the parts of them that I want in the right places. Hopefully that's helpful. Graphing piecewise functions can be a little bit of a pain in the butt. If you need to, you can totally graph all of the pieces separately and then be like, okay, I need this piece here, and I need this piece here, and for y equals 3, I need this piece here. And then you can put them all on one graph. The last thing I'll say is this is a function, right? It totally passes the vertical line test. There is no vertical line that hits more than 1. Now, if someone did something, I don't want to say stupid, but if someone did something atypical and maybe put like an equal sign right there, that would mean this function was defined to be 3 when x is equal to 2 as well, and it would fill that in. And then that wouldn't be a function anymore, because when x was 2, y could be 3 or 4. I can't imagine your teacher's actually going to have, like, no one's testing you on this. It's a dumb kind of thing to do. Like, no one's trying to trick you into thinking a piecewise function is actually not a function, or vice versa. But it just seemed like a good place to say things. So, yeah. All right. If you didn't already, please make sure you fill out the attendance form so I can mark you. If you get marked absent accidentally, just let me know. We'll take care of it. And yeah, have a nice weekend. I'll see you all on Monday.